Hello, thank you for joining us today. My name is Gabriel Escalante, and I'm part of the Syntica marketing team. Today, we have an honorary guest, Dr. Bruce Young, and we're going to be asking him a couple of questions just to get to know more about his research and his career. So, thank you for joining us today, Dr. Bruce Young.
My pleasure.
So, for starting, we're going to go with the first question. This one is what is your educational background? Where did you go to school, and what was your mascots?
Well, I did my bachelor's degree at Washington State University, my master's at Northern Arizona University, and then my PhD up in Canada at the University of Calgary. And to be honest with you, I don't know the mascots of any of the schools. That's really not why I was there. I had the pleasure of working with Ken Cardong at Washington State University, at George Goff at Northern Arizona, and Herb Rosenberg at the University of Calgary, three really good anatomists doing very different things. And that's what occupied my time.
Yes, I imagine there was a lot of studying in between, your undergrad, PhD. Uh, Definitely, it must be interesting. So, with that, will lead to the next question. So, this is more of a personal one. What was the moment that you knew you wanted a career in the science field? What drew you to this specific field that you're in?
Well, I think I'm very fortunate. I was essentially born to do this job. I grew up, my father had a large library. Most of it was science, a lot of animal. I grew up reading from his library and playing out in the woods and play. Even at 6 or 7, my parents would let me loose and to go play. Most of the time playing, it was like catching frogs and catching snakes and just interacting with animals as much as I could. And I was fortunate, I just never had to stop doing that. So I never really had a defining moment when I knew what I wanted to do. I just knew I always wanted to do science and always wanted to work with animals.
Yeah, that's good to hear. Animals are definitely part of in my opinion, animals are some of the beautiful things that you can find in this planet. I too am passionate about animals, and I, as a matter of fact, wanted to be a veterinarian in the past. Uh, but I found out that I'm allergic to cats and dogs, so I had to switch my career path. And
Understandable.
but enough about that. So let's move on to the next question. So, how did you get your job? What jobs and experiences have led you to the present position that you are currently at?
Well, I'm currently a professor of anatomy at the medical school where osteopathic medicine was founded. And that's a great thing if you're an anatomist, because anatomy is kind of the foundation of osteopathic medicine. So this is, I think of this as kind of the cradle for anatomy in medicine. So it's a perfect fit for someone who loves anatomy. And I'm very fortunate here that pro research environment. I mean, as a good example of that, it took me a let me house adult alligators here. And that just gives you an idea of how cooperative and encouraging they are of research. So I was looking for an opportunity that would really allow me to diversify and expand my research while allowing me to teach what I love, which is anatomy at the highest level possible. And this opportunity really was perfect for that. I had worked at a number of institutions before, always teaching anatomy with some and doing varying degrees of research. This was just kind of a nice thing where my needs aligned with their needs, and it's been a really wonderful fit so far.
Thank you for that answer. Very concise. Let's dig in a little bit more on your about your research. What would you say is the real world application of your research? What makes your research so important? We're just curious to know about the details, and you definitely have a very rich background in the science. And as I can see in the back, you're passionate about research and crocodiles in this case.
Well, my passion is much more for the research than the crocodiles, frankly. What I'm particularly interested in right now, and the focus of my lab, is to understand the fluid dynamics of the cerebrospinal fluid. This is the fluid that bathes, nourishes, and cleanses the brain and the spinal cord. And we know it plays a critical role, but the interesting thing is we don't know, and when I say we, I mean science as a whole, we don't understand how the fluid moves around. We're not clear completely on where it's made and where it's absorbed in the body. And I mean in humans or anything else. At the same time, we understand more and more now that the cleansing function of the CSF is something we probably misunderstood. So, for example, there's been a lot of recent claims that even diseases like Alzheimer's may actually originate. If it's not essentially percolating through the brain appropriately, it may not carry enough waste away, and it may be the buildup of those wastes that lead to Alzheimer's. More and more mathematical and physical modeling of the CSF suggests that a lot of other neuropathologies, things like cerebellar herniation and syrinx formation in the spinal cord, may ultimately be due to disorders of the cerebrospinal fluid. So there's a lot of really interesting work to be done. The challenge is, of course, it's mainly medical applications, but in some ways, this is work that's hardest to do on humans. To get real good data, you want to have direct recordings of the cerebrospinal fluid. But that means drilling through the skull, implanting things around the brain, or doing really deep surgery and implanting things around the spinal cord. And obviously, we can't do that to humans in most circumstances. There are a few direct recordings we can take of patients that have suffered, say, a traumatic head injury where the skull's already been compromised, but then their system's a little abnormal just because of the unfortunate trauma they've suffered. So I prefer, instead of trying to look at the little bit of human data we can get, I prefer to use an animal model. And after consideration, I felt that the best animal model for my surgical work would be the alligator. And that may sound like a really odd connection, but we've known for a long time from our work with humans that the physics, the influence of the CSF comes from two things. One is our cardiac output and the arterial pulsations. When little arteries in the brain pulse, with each heartbeat, it causes the CSF to pulse. You can see that if you remove a little bit of the skull, you can watch the dura, the membrane that surrounds the brain and holds in the CSF, the dura will pulse. So we know that cardiac output plays a role. More recently, we've had pretty good evidence that the ventilatory cycle plays a role. So every time we inhale and exhale, the CSF moves a little bit. But on both of these, we don't really understand how. It turns out that among all the vertebrate animals we know, alligators have the most plasticity in their cardiac output and in their ventilatory output. An alligator, unlike us, can just decide to hold his breath and do so for hours. And he doesn't have a lot of compensatory mechanisms. Well, if you want to understand how ventilatory cycle influences CSF, this is great. Because what I could do in the middle of my surgery is I can just turn off my ventilator and stop all airflow, stop all ventilation, and my alligator's great. He could do that for hours. If I was doing this on a cat or a dog or a mammal, I just don't have that flexibility. At the same time, the alligator has a unique set of valves in its heart, as well as unique valves outside of his heart that allows the alligator to consciously redirect blood flow through his body. He can choose, and I mean that term literally, he can choose not to send much blood up to his brain. It's a very unusual system, but associated with that, he has a lot of tolerance for things like hypoxia that mammals don't have. So again, it's a great research model, because if I want to tease apart the cardiac influence from the ventilatory influence, I can literally go in surgically and just stop all the blood flow to the brain and record for a while what's happening. So for those reasons, predominantly, I've been focusing my work for the last several years on understanding the cerebrospinal fluid of the alligator.
That's fantastic. I was not aware that alligators were able to do such complex decisions. I would say I'm not sure if it would be called decision, but wow,
Yeah,
that's
I don't know the right term for it, but we know they are voluntarily controlled valves. It makes sense for the alligator's point of view. If he wants to, say, grab a prey item, which is what they'll do, then hold it underwater for hours and drown it, he can do that, and he will redirect the blood so it's not going to his lungs because they can't use them underwater, and share it with the rest of his body. And so it is, for lack of a better term, kind of a conscious. These valves are actively controlled by the alligator. It's not a reflex action. So
It's
it's a very
interesting.
fascinating thing.
Yeah. Would you say that that was the case in Florida back? I'm not sure which year it was, but it started to snow, and the alligators were in some state of I'm not even sure what the word is. Like they just got their snouts out of the water and like yeah, you know what I'm talking
Oh, I
about.
know exactly. It was such an amazing evolutionary scene because we tend to think of animals as learning their behaviors and learning their coping system. Where these alligators were, it hadn't froze like that in decades. So this couldn't have been a generational thing. These alligators that were all carefully putting their snouts up above the frost line couldn't have possibly learned that behavior from any older alligator. This was a deep genetic physiological response that they knew when it got cold enough, that's how you live. And seeing that kind of thing play out is really interesting for someone who tries to figure out how animals work. Understanding how deep rooted that behavior had to have been, those images were fantastic.
Were you able to see one in person?
I did not. No, and my
Yeah.
animals are kept very warm, very comfortable. I have almost a spa for my alligators. They've never been exposed to the freezing.
Oh, it's good to know. I was more meaning like if you traveled down to Florida just to see if you had the chance to witness it, because it must have been
I
a
would
sight.
love to see it, but I just wasn't there right during that cold snap.
Yeah, yeah, that's fantastic. Thank you for sharing uh, all about your research and well your passion as well. Let's take a little bit more with your research. Well, having the fact that you work with crocodiles, what would you say is the most challenging part of your research, and simultaneously, what would you say is the most enjoyable part of your research?
Well, for me, they're really the same thing because of the kind of unusual nature of my research program. I have to design almost every experiment I do from the ground up. There's no piece of equipment that's built specifically for doing surgery on alligators. I've even had to have some of my surgical instruments specially crafted for me. All of my surgical tables, almost everything I use has been custom built just for this work. Because we don't have a lot of technology for directly recording things like CSF flow, because it's just not done in humans very much. Even some of the equipment I use, I've got to find ways of tweaking somewhat or modifying because it wasn't designed for this. And frankly, I love that kind of challenge. So to me, having to build a whole lab up from the ground up for my specific research program is very frustrating at times, but it's also very rewarding. I enjoy it.
I bet challenges are often what makes us adapt to the situation, and I do as well
Exactly.
enjoy that kind of that those challenges. It's interesting
There's a
how we
lot of
adapt.
there's a lot
No,
of
go ahead.
really good science that can be done using commercially available kits. A lot of molecular biology, a lot of cell biology, and I don't mean to dismiss that in any stretch, but there's nothing I do that I can get a commercially available kit for. Everything has to be kind of custom crafted.
Thank you. That's sounds very challenging, first of all, but rewarding at the same time. Having that in mind, what would you say is the most defining moment that you've encountered in your research?
That's a tough question because I think there's been a lot of them. One of them certainly was when I was a freshman and went to university for the first time. I met Ken Cardong, who was an anatomist who specialized in venomous snakes, and started working in his lab. And to say that I was hooked is an understatement. I mean, Ken became my academic and we worked together the rest of his career. So that was undeniable. But there's been other moments that have just been, just that stick with you, shall we say. I did a study once. For a while, I was studying the physics of sound in snakes, how a rattlesnake rattles, for example. And king cobras, when you get a king cobra angry, it makes a very deep sound. It sounds like a growling German shepherd. It's not at all like a snake. It's a really guttural sound. It's very intimidating because of just the size of the king cobra anyway. And no one had ever explained how it's made. So I looked at the anatomy and I found there were little resonating chambers, little anatomical pouches off of the trachea. And the trachea is almost a third the length of a snake's body. And so essentially what this king cobra was doing is when he growls, he's blowing across like the top of a beer bottle. And that's what's making that low. But of course, it's one thing to propose that. The question is, how do you experimentally test it? And you experimentally test resonance in part by changing the density of the gas, right? If we take a hit from a helium balloon, our voice goes up. I got large, very angry king cobras. I would taunt them till they were growling at me. Then I would grab them. I would stick a tracheal tube in them and I would flush their with helium and then quickly turn them loose. And he would make this adorable little Mickey Mouse growl at me. which I will never forget. It would be really funny if it wasn't for about a 12-foot snake that had the ability to kill me repeatedly, and then to have this thing make this little high-pitched growl was just, that was a lot of fun. I designed an experiment once when we were to study the physics of spitting and spitting cobras. It's an interesting system because the snake from about, I'll say 7 feet away is wonderfully accurate, in my experience, a little over 95%, at hitting your eyes with the venom it spits. And it is venom it's spitting. The venom has a biological acid in it, will just dissolve the cornea. So it's debilitating in terms of pain, and it will cause blindness. So it's a fascinating defensive behavior. But the question was, how can the spitting cobra hit the eyes? So I collaborated with my good friend Guido Westhoff and with Horst Bleckmann, who ran a neurophysiology lab at the University of Bonn then. And I designed the experiment. We brought out everything over and we used a series of lasers and a special little computer chip I had built that I wore on my head. And what we found, what we were able to show, is that the spitting cobra can actually watch and track my movement dimension. And then, like a pro quarterback, he's guessing where I'm going to be in the next fraction of a second, and he actually spits in that spot in anticipation. And then at the very last minute, he wiggles his head just a little bit to pattern the venom and maximize his chance of hitting my eyes. And by a whole series of very complex surgeries and experiments, we were able to put all of that together and demonstrate it. And just designing that and get together with two good colleagues and doing these very long, complicated experiments, the first time it worked was just wonderful. So there's been some really neat moments. More recently in my lab, we were able to show for the first time that a little skeletal muscle, a system called the myodural bridge, we have the same thing. If you electrically stimulate it, it causes the CSF to flow. It's almost like a little CSF mixer, a little pump system. And people had speculated on that, but my lab was the first to generate experimental evidence for it using alligators and some careful probe surgically implanted around the brain. And that was a special moment to see that all come together.
Well, I bet it sounds like first of all, it sounds like a lot of fun to create such experiment, and well, you have to think outside of the box. I imagine it's it's
Yes,
good to
indeed.
hear. It sounds like a really good. It just sounds plain amazing. I'm not gonna lie. Like I'm an animal enthusiast as well. It's just interesting how Mother Nature has created specific animals to adapt to the different situation. This about the spinning cobra. It's I was not aware. I was aware that they would track your eyes, but not to that extent. It's fascinating. Would you say that? Well, you mentioned a lot of surprising defining moments in your research. But would you say that one of those in particular is one of the most surprising scientific findings you've encountered, or one that you would consider the most important?
There's been a few others. In terms of the most important, probably in terms of impact on man, the recent work on the Myodoro Bridge is really interesting. Another one that was surprising, I should have anticipated it, frankly, but I didn't, to be honest. I was doing some work with big Western diamondback rattlesnakes, and we were looking at the neural basis of controlling their venom. So when they bit, could they figure out in that tiny fraction of a second when the fang was in, did they have any control over the venom or didn't they? So I surgically implanted a special sensor around their venom duct. You had to have a big enough snake so you could do this. And then I would get them to bite live rats. What I found was fascinating. After they struck, as the venom was injected, then they literally kind of created negative pressure and sucked material back up. Some of their venom and presumably some of the interstitial fluid from the rat as well. It kind of makes sense. Their venom gland is almost like a pipette bulb. So it's a blind ending system. So if you squeeze it with muscle and then relax the muscle, there should be some negative pressure. But no one had ever thought of that. And that experiment's still the only time anyone's ever figured out a way of directly measuring and watching the venom flow through the system. I should have thought that there was going to be negative pressure, but I freely admit I didn't. It was all of a sudden to see it on the traces, it was like, oh yeah, of course. And that was a lot of fun.
Sounds very interesting. Would you say that it's like a vaccine? Like I understand that sometimes when you have the vaccine, you have to suck a little bit of the blood and then inject it as well. Would that how it would be, or not really? Because
It's
it sounds
probably
interesting.
not quite the same thing because that's often done just to make sure you're in a blood vessel. The snakes don't care if they're injecting into a blood vessel or not. But the neat thing about it is it may play a real big role in some of their sensory systems. You know, the rattlesnake has the ability to inject into a mouse in the field and then just let go and track the mouse later on. It may be when he pulls this system back in, he gets all sorts of sensory information about a particular mouse and a unique signal that he can then track in the environment.
Interesting. Yeah, a lot of things to think about with everything that you mentioned. Wow, I never expected this, but thank you for sharing that. It's definitely a very
My pleasure.
interesting scientific finding and achievement. Um, so let's move on forward. We're still with your research, which I'm enjoying a lot. Um, what do you say that you would want to achieve with your research? What would be your end goal?
Well, what we're working on right now, and we're getting very close to it, we want to form a complete mathematical biophysical model of how the CSF flows in the alligator so that we can say under any size alligator, under kind of any condition, what pattern, what movement of CSF would we expect? Where I would think probably we're only about a year away from that now. And once we can get that, I can do a lot of experiments to verify that. And then what we're hoping to do, and this may sound like a bit of a leap, but given the science we're using, it's really not that far. We want to morph that model and apply it to humans and see just how good of a fit we can get. The same basic techniques would all apply. And then the ultimate goal would be, can we use that model to try looking at some of the human neuropathologies and get a better idea of what's actually causing them and perhaps even a better idea of some possible remedies for them.
Thank you for sharing that. Um, it's a lot to take in, but it's a really nice end goal, and I'm looking forward to seeing how your research ends. I'm really excited to see
Thank you.
how everything works out because I'm positive it will work out. Um, you touched this a little bit in earlier questions, but we just want to know what are one of the coolest things about your work and your research. You mentioned about the challenges, but is there any other particular
Well, I'd say
fact?
there's a couple things to it. Certainly, the animals I've had the pleasure of working with are kind of cool. At least I think so. It's a novelty. I don't do it because it's a novelty, but as a scientist, it's very interesting. I mean, we know so much less about something like a spitting cobra than we do about a lab rat. So there's a void there, and I like feeling that I'm kind of working in that void and helping to fill that in. And frankly, there's things there that we don't understand that could have a lot of potential. The alligators I work on, for example, have the ability to perform neurogenesis throughout their life. In other words, within their brain and spinal cord, they can make new neurons all the time. We can't do that, or at least we can only do it in a very limited basis. And that means things like spinal cord repair in an alligator may be very, very different from what they are in man. And we really only know what it's like in mammals. Maybe if you study what it's like in the reptile, you may learn some unique clue, some guide that could really inform human medicine. And so I find that ignorance, for lack of a better term, about so much of these lower vertebrates and reptiles to be kind of compelling. So that's one of, I guess, the coolest things. Another cool thing does relate back to challenge. I like the fact that most of what I work with, I've had to handcraft or modify in some really fundamental ways, or use in not the way it's designed to being able to take that and use it in a unique way, but to get valid publishable data out of it, I really enjoy. I like that challenge.
Thank you for sharing that. Definitely working with exotic animals is it's a lot of fun.
Mm-hmm.
I share your feeling with that. Um, so we mentioned a little bit as well about some of the challenges that you have faced in the lab, but is there any other challenges that you might want to expand? Maybe getting your exotic animals, if
Well,
you can share, of course.
yeah, there's several challenges I face with just the way I do my work. One is, of course, I have some safety issues that most people doing this research don't have. I've spent my career working on venomous snakes. The alligators I work with are large enough to be human. So there's issues there. The downside of keeping a colony of alligators to use on surgery, and right now I'm training them to run on a treadmill, which turns out they don't do voluntarily very well. That means almost every day I have to wrestle with alligators, which is not something that I was taught in graduate school. So there's definitely a challenge that way. Almost all of my surgery is microsurgery. So it's almost all done under a microscope. The area that I have to get a probe successfully in to record the CSF is, generally about a millimeter or so. And not only does it have to be placed right, but it has to be placed in a way that it's fluid tight. Because if there's any leakage, any little error in the surgery, the integrity of the system's destroyed. So there's a distinct challenge that way. And then just having to design the experiment in a way, there's not a lot of reference. If you're working on mammals, you can go and look at the body of literature on how people approach this problem in a rat or in a cat. If you're working on an alligator, you don't have that luxury. Something as what sounds as simple as figuring out the surgical approach I'm going to take to implant my probe, there's no guide for that. So those are kind of the biggest challenges to my work.
Would be like do it yourself in a matter. Yeah.
Yeah, I
You get
enjoy that, but there's no question that it's a challenge.
Definitely. I can imagine. It's yeah, I know. I can't imagine. I take that back. It's a lot of fun though.
It is
And
a lot of fun. I can't pretend that I don't enjoy my research very much. I often, and I don't like to admit this to my administration, I often feel like I'm being paid to play in my private sandbox. And that's a pretty good way to make your living.
absolutely, I agree. I definitely agree with that. um, So you mentioned a little bit about your equipment and how you have to adapt it. Would you be able to expand a little bit more on what kind of equipment you use in your lab?
Well, I have a lot of what you would think of as kind of basic neurophysiology and physiological recording equipment. So I've got an extensive bank of like grass amplifiers and stimulators, which I really like because they are very reliable, very robust, and you can use them in all sorts of different ways. So I really like that. I've got a number of high-speed digital video systems that I can record whatever behavior I'm looking at. What the most recent addition to my lab that we're going to start doing the surgeries on soon is the industry's Doppler flow system. And I picked this just because of the versatility of it. I really like how it was designed. There's a big challenge if you're going to record the CSF, in that, of course, not only is it encased in the body, but if you want to look at the flow, it's non-oncogenic. So it's tricky that way. And I'm particularly interested in looking at movement and how movement might influence this. So I can't do it with MRI, which is the popular way of doing it. So what I'm going to try to do is surgically implant the Doppler flow velocity probes that Indus makes and use those to directly quantify the CSF flow around the spinal cord. It's never been done. But I think the alligator's a viable way to start with that.
It's a very think outside of the box use for the equipment. It's fantastic, and I believe it will work. So keep us posted.
I
Yeah.
I'm quite confident that we can make it work. We've got a little microscopic glass bubbles that can render the CSF echogenic. So far in all my trials, it's worked quite well. Now we just have to try it in the living animal and see how it does, both how I do and how it does.
Yeah, thank you for sharing that. Um, Very exciting for your research, I imagine.
Mm.
Let's move on for maybe an advice for young people that are interested in a similar career path that you're in. What would you tell them, uh, or what would you tell
No,
yourself
I
in the past?
it may not be the most popular advice, but I kind of follow Hardy in his classic A Mathematician's Apology, if you're familiar with it. And that is to say that curiosity, follow your curiosity, follow your passion. There's oftentimes such pressure in science to make sure that you can justify what you're doing and that it's highly fundable and it's directly related to something else. I think you're better off following what you're excited about and let your own curiosity. If you're a good scientist, your curiosity will lead you to things that are of value to other people. And I think that's all science really should be doing.
Yeah, thank you for the empowering words and very wise as well. By any chance, do you have a role model that you looked up or you still look up to? For me, as an example, is Steve Irwin, or was Steve Irwin, and he definitely helped me out in how I shaped out to be. Like I love animals and I care for them, and just I'm curious to know if you have any role models.
I don't know if I'd call them necessarily role models. I'm fortunate that I work with a number of research collaborators that I genuinely admire. They have different talents than I do and different perspectives on things, and we generally work quite well together. The individual who had the biggest influence on my own career was Ken Cardong at Washington State University, who I met when I was, I think, 17, and who really shaped my future career path.
Yeah, thank you for sharing your well, how do I say it? Uh, well, thank God this is recorded, so this can be edited out. Yeah, thank you for sharing. Well, about your past,
If
and
I if I
Yeah.
could skip a direct role model and look at kind of history, the anatomist that I would love to be, I'm far short of this, would be Thomas Henry Huxley. I mean, just his towering intellect is far beyond mine. His influence at his time was just amazing, and the breadth of things that he was curious about and what he looked into. If all anatomy and all science was done like this, we'd be in a different place in society right now. But unfortunately, Thomas Henry Huxley's don't come along very often.
Thanks. I'm not too familiar with this scientist. Definitely will look him up after this session. So let's move on to the future of your research. What comes next?
Well, like I say, we're going to move a little more into what's called computational fluid dynamics. So start the mathematical and biophysical modeling of how the CSF moves. I want to use that not just to make a model, but to directly predict and design experiments to test real subtle aspects of CSF flow. If the CSF forms a vortex right around one region of the spinal cord, that would likely induce pathology in that part of the spinal cord. Being able to predict that and then demonstrate it using something like a Doppler flow probe system, where we could show the dynamics of the flow pattern, would be really powerful. So that's where I would predict probably for the next 4 or 5 years, my research program will be focused on getting that model created, verifying it, expanding it, kind of using it as robustly as possible to inform and direct some of the next experiments.
Thank you. There are big plans ahead. Then it's good to hear.
There
It's
are.
good to hear for your research. So we have reached the end of our video, and I would like to thank Dr. Bruce Young for sharing his experience, his research, and definitely wise and empowering words for future generations. Thank you very much for joining us today, Bruce.
It was my pleasure. Thank you.